Hi, Bianco. How are you?
Hey, Sajal, how are you? Can you
Good,
hear?
good, good. Thanks for your time. Thanks for making it.
No, my pleasure. Thank you.
Okay, so I think we should start.
Okay.
Yeah, so other people will join, perhaps.
Mhm.
So please start.
Okay, so uh, welcome back, everyone. Today's lecture is the second part of this series of lectures on differential cohomology and gerbs. So last time we maybe we briefly review what we discussed. So we started from principal G bundles and looked at check cohomology, and from that we pulled out a bunch of characteristic classes. For example, by looking at this exact sequence, short exact sequences of groups, we could obtain the first Strafford-Whitney class and the second Strafford-Whitney class and the first Chun class and even the Dixon-Duality class, which is the characteristic class for gerbs. Then there was a question last time, which was that so this degree 2 integral cohomology classes are represented by line bundles. So these are geometric cocycles representing cohomology class. And then the degree 3, we didn't really learn about this, but I gave you the answer that the S1 bandit or U1 bandit gerbs, which is the topic for the third lecture in next Monday. So those classify degree 3. But then if we have some connections on your bundle or higher line bundle, so this is L, which is the S1 bundle with connection, then those things are classified by degree 2 differential cohomology and gerbs with connection, and degree 3 differential cohomology, and higher gerbs with connection with the higher differential cohomology group of your base manifold. So today's topic is to learn about H hat, what H hat is, and how we can understand and looking at the hexagon diagram of differential cohomology. Okay, so let me begin with some notations. So M is going to be a smooth manifold. Sometimes it might be better to say compact smooth manifold, but I'm going to just say smooth manifold. And I'm going to use this notation C to the K. Sorry, what happened to this? Of M with coefficients in R, be smooth singular K cochains in M with coefficients in R. Here R is a commutative ring with unity. And this is sort of some typical notation in homological algebra, but in case some advanced undergrad students might not have seen this. So these are smooth, singular, K cocycles in M with coefficients in R. So a cocycle would mean is a K cochain such that the boundary map from, you have seen this in last lecture for check homology, right? So for this map, so if we have some, let's say, chain C, then this boundary map gives you the image. And if this is 0, then we say this is cocycle, right? And omega to the k of m, as always in differential geometry, differential k forms on m, real differential forms. And well, this smooth manifold is also real manifold. And this notation.
Sorry, Bianco.
Yes.
Can I ask one question?
Yes. Yes.
Single
This thing to be harm c to the c sub k of m to r, right? So yeah, don't get confused. This is cochain, not the chain. Is that good? No
there is
problem.
one thing though. When you say smooth, so like how do you define smooth here? So from
It's not a big problem because, as you see, like only thing that matters here is like this kind of k simplex, and then m, and then yeah. I mean, if your question is from this thing to be, I mean, this thing has corners, and so then you're asking, what does it mean by smooth? Then, yeah, you have to massage a little bit about the
right.
the
Yes.
topology definition. Yeah, but
Okay. Thanks.
those are my
That's
minor.
exactly
So, yeah, those are minor technicalities, but I think that's a fair point. That's a good question. Yes.
Thank you.
Yeah, no problem. Okay, and then I'm going to introduce this notation. You probably haven't seen this that many times. So this subscript CL means closed, so declosed. And I'm going to put another subscript C here. This means closed K forms with integral periods. So that means if omega is an element in this set, if and only if the following holds. So closed means the omega is 0. Then if you, I mean, this integral period would mean if you take this differential form and integrate over, let's say, here some blank, integration of differential forms is a pairing of differential form and some chain, right? Then the chain is a blank. So but then I mean, the domain of this thing would be taking all the k chains. If this is k form, then it gives you a number. But then I'm gonna restrict that to k cycles, degree k cycles of m. Then this should have value in integers. So that's what it means by closed k forms with integral periods. By the way, we are going to see this kind of map pretty often today. So you're going to have lots of opportunities to get familiarized with this thing. Okay, now another notation is that I'm going to use this twiddle to say this projection, applying R going to R mod C, is mod out by C. And so this fact is going to be useful, which is that lambda would be a proper subring of R. R is the set of all real numbers, a ring of real numbers. Then a non-vanishing differential form does not take values in lambda. So this is quite obvious fact from what it means by a differential form. Basically, what is a differential K form? Then you consider this tangent bundle, and then consider the dual of tangent bundle, so cotangent bundle, and then you take sections. Or you first take exterior product for K times, and then take sections. Then if you feed in K vectors, then that gives you some number. Then if the differential form having a value, for example, if this is sort of all integers, then you can have a differential form that has values only in integers. That violates the definition of what it means by differential forms. So it's an easy check, but this is going to be useful later. And this is a fact that this map from differential K forms on M that goes to C to the K with values in R mod C. So how do we define this map? Take differential K form, and then you integrate. So that means if you record the proof of drum theorem, so basically drum theorem is saying what? So you say you have a drum complex of differential forms and then cochain complex on your manifold. And then on the same degree, you take differential form, and then basically you take this integration of differential forms and then fit in chains. So make this as a cochain. So that's the integral map in there. It's the same sort of thing. And then you model by integers. So then this map is one-to-one. So this proof is not difficult. You just need to think about this using this fact. So these are some preps, like setting up some notations for the main thing. So now I'm gonna just go ahead and define Chigger-Simons differential characters. So this set h hat to the k of m is defined as follows. So this is a collection of our pairs chi and omega. Here, chi is a map from k minus 1 cycles on your manifold that goes to R mod C. So you can view this as like a group homomorphism. Then here omega is simply a differential k form. Such that this chi and omega should satisfy the following. So if I first, let's say for every k chains, let's say d in degree k chain group, integral chains. So I take first the chain and then taking boundary and then taking chi. So clearly this is a k minus 1 cycle, right? And then this thing should be the same as integration over integration of omega, this degree k differential form, over d. And then because this is going to give you real cochain, so you should sort of match things. So here you write mod C. So this should be satisfied. So collection of all these pairs is differential characters, and then the group structure is just simply an addition on this element and addition in this element. Components-wise addition. Character, the group of differential characters, or differential cohomology. Of m with degree k. So that's so differential cohomology. So this alone is I don't know, maybe not very motivating. So I think it's going to be better to see the following very well-known thing. It's called differential cohomology. Hexagon diagram. So here's the diagram. So this H hat K of M sits in the middle, and then there are maps. There's one map whose name is I that forgets the differential datum. So it gives you just integral cohomology. Then there is another datum from R map that gives you some sort of characteristic forms. For example, if you have a line bundle, then it gives you the curvature form. So it lands in degree k closed forms on M with integral periods. So that's why I introduced this notation. And then with these closed forms, you take drum cohomology class, and then you basically take a real cochain, then you have a map into degree k real cohomology class. And then there's this map from if you consider this short exact sequence. So this sequence of groups induces the corresponding sequences in cohomology. So this is a part of that map. So I'm gonna call this R for the realification of the integral cohomology class sitting in the real cohomologies. Then I'm gonna erase this. And this map is onto, and this map is also onto. And if you look at the corner of the I map, sorry, let me first say corner of the R map. So then it becomes this cohomology with 1 degree less on M, but then your coefficients are sitting in R mat C. Then, so then this is corner, so it's injection. And this map is minus B. And here B from Bockstein. It's nothing but the connecting homomorphism if you have this map C0 into C into R mat C into 0, that induces a sequence in cohomology groups. Then from here, the 1 degree up, the connecting map is this Bockstein. And then for technical reasons, we have minus. Then if we look at the corner of this I map, so people usually call this A map, then you can easily define a well-defined map from k-1 differential forms on manifold. But then this map has a corner, which is the same degree forms, but closed with integral periods. And then we have this exact sequence. Then on this corner, we have 1 degree less real cohomology. And this map is just taking representative of your cohomology class. Then that map is well defined, as you will easily see. And this map is sort of easy. It's also coming from the sequence, or you can think of it like the image of this sitting inside here. So there's this edge. This is simply the taking differential of your differential form. So this is the hexagon diagram of differential cohomology. So all these triangles are commute, and square diagrams commute, and diagonal sequences are exact sequences, and upper sequences, this is a long exact sequence, and lower sequence, this is also a long exact sequence. So I'm going to write it down. Squares commute, diagonal are short exact sequences, and upper D and lower sequences are long exact sequences. Yeah. So from this, we can capture lots of information about what this is actually meaning. So I think it's worth looking into details, like how to make sense this hexagon diagram. So that's actually the main technical thing that I wanted to do today. So proof. So this proof is going to be consisting of lots of exercises for students, for example, or anyone who's interested in filling in details. So to save time, I'm gonna leave many claims into exercises. But if you go to my webpage, there's a part that I post some slides and notes from talks, and then if you go there, it's not there right now, but soon I'm gonna post my notes and this version, I'm handwriting, and also the text version. So in the text version, I'm gonna include all the necessary details so that you can check if needed. Okay. So because the diagram is huge, it actually consists of multiple steps. Yeah, that's correct. That's my webpage. Yeah. So I and R maps. So let's just focus on these two maps for now. So we need some algebras. So let's say A1. So any subgroup of a free abelian group is free, right? And A2. So this is definition. An abelian group G is called divisible if for any x in G and any n in positive integers, there exists some y such that x equals to ny. So it's just definition. Well, whether or not you have seen it before or feel like you feel it and you think of it familiar or not. So it is a definition. And this thing is a proposition. If G is divisible, if and only if um, G is an injective object in the category of abelian groups. So, i.e., G is an injective module. Well, I would say this. If you can think of a proof uh, right now, that's I think could be natural because I mean it's been a while. But I recur a proof of this requires a use of John's lemma. So I don't think this is kind of something obvious at the very least for geometers and topologists. Anyways, so these are some ingredients we need. So now take an element chi omega in h hat k m. So then, what is chi? This is a map from, sorry, k minus 1 cycles of m into R mod c. So then, we note that this is a subgroup of degree k minus 1 chain group, right? So what is a chain group? So it is a group generated by R maps from k minus 1 simplex into M. So by A1, this is free, right? And this is a some sort of undergraduate or graduate level algebra fact, often appears in qualifying exams and etc. If the group is free, then this is projective. This is projective module. So then what is good if this is projective? Well, if we have a surjection, let's say R, that it goes into R mod C, then there exists a lift such that this commutes. So this red dotted arrow now is because the module is projective. Now, I'm gonna call this chi bar, and then put it here. So this is chi bar. And notice that this is actually divisible. So this is an example of a divisible group. So then this is an injective object. That means if there is this injection, into, I mean, this degree k minus 1 cycles are sitting inside degree k minus 1 chains, right? Then there exists this lift. So I'm going to say this to be T, just to match with the notation in Chigor-Simon's original paper. So then, if we consider this T, right, and then we restrict it to cycles, then if we take modulo Z, then that is exactly the chi we started with, right? So we have this in mind. Um, Now let's look at this the co-boundary of T and then twiddle. Why? Because this is actually the same as co-boundary of T twiddle applied first. So if you're curious why this holds, then this is actually composition between T and then boundary map. Then if you first take parentheses here, then that is this. Then if you take parentheses here, then that is that. So then you can view this as T twiddle composed with this boundary. Then this must be then, if you think about what it means by chi, by definition of this pair, the definition, this must be integration of omega mod integers. So this we can say this co-boundary of the real cochain T, right? This T is real cochain because it takes chain that goes to reals. This one is the same as the integration of omega, let's say minus some c, where c is some integral due to k chain. Okay. So if you're an expert in this area, you probably have seen this formula more often than this thing, because in many papers this appears basically like some topological datum and differential geometric datum, and then there's some homotopy that captures the discrepancy between these two. So that's what the meaning of this formula is. So this is an aside because I just talked about this. You can even define a differential cohomology using these triples. Let's say this C is a topological data, and this T homotopy data, and then this omega a differential form data. So taking this triple, and then you should impose appropriate equivalence relations on these triples, and then can define the same sort of differential cohomology. Actually, this is actually done by Hopkins and Singer. Basically, they wrote a landmark paper that first appeared in 2002, and then the published version appeared in 2005. 2005. Sorry. Then, if you look at chapter section 3 in that paper, it talks about their construction of a differential cohomology using this triple, and then they even proved that this pair model is the same as theirs. Yeah, I'm going to just continue. There's one. There are several other remarks, but let me just focus. So now note, if you take co-boundary again, then it's 0, right? Because d square is 0. Then this co-boundary outside that commutes with integral, so it becomes the W, sorry, d omega minus delta C. So we see this d omega equals to delta C. But then I'm going to say this is a star. And what is the star? Is this. I said this is going to be useful. So if lambda is proper subring, differential form cannot take values only in lambda, right? So now you see this is real differential form, and then this becomes real cochain, right? Then this is integral chain. So their being same must mean that this differential form d omega should be identically 0, and so is this coboundary of C. So now here's an easy exercise. Verify that this omega is actually in the pair chi comma omega, that omega lives in degree k differential forms closed with integral periods. Well, if this is easy, why don't I just say that one line proof? Yeah. So if you have omega and integrated, then you restrict it over C. Sorry, this C is not that C. So this C sub k of m. Then basically what you have to show is this has values in reals. In integers. That's what it means by having integral periods, because closeness is already done. So then from the formula here, what you see is this is the same as C plus delta T. Then if you restrict this thing in k cycles, then this has to vanish. So basically, you should have values in integers. Okay. So now we define this. Now we can define the map I and R like the following. Maybe here. This is I map that goes to integral degree k cohomology. So you take chi and omega from construction. You know what this C means, right? And you take the integral cohomology class. I mean the cohomology class of that. Why can we do that? Because C was integral k chains, but here we have seen that this is k cochain, but we have seen that this is k actually cocycle, so that represents degree k cohomology class. Then how about this R map that goes into degree k forms with integral periods? You take that and map it to just omega. Just take the second component. That's it. Then we need this exercise. So, graduate students, I mean, it was actually same for me. When you try to define something, right? maybe when you're in undergraduate, you never, you rarely see things that is not well defined. Most of times things are well defined, but um, if, um, in mathematics, if you trying to construct something and if you make any choice, then it is your responsibility to show that your theory doesn't depend on your, the choices that you made. So here, when I define this C map, uh, is that independent of choice? Actually, not. Actually, it is actually depending on the choice. So here, I chose this lift to figure out what the T means. And then only after I know T, then I could figure out what the C is. So I should prove that verify the well-definedness of I. R map is not necessarily, but this. Independence of choice of lifts. Because in algebra, as you know, in projective module, injective module, so that says the lift exists, but it doesn't guarantee that those lifts are unique. So then let's do that work. It's going to be short. Let T prime be another lift satisfying delta T prime equals to integral omega prime. Here I don't actually need to distinguish, but I'm going to just follow the paper by Cheever-Simons. So then, if you consider this T prime and T, then if you take minus and then restrict it to degree K minus 1 cycles, and then take modulo Z, then that becomes 0 for obvious reasons, right? Because this one thing alone should give you back chi, and this thing also should give you back the chi. So chi minus chi is 0. Then we may rewrite this as follows: T prime equals to T plus delta S plus D. Here, D is degree K minus 1 integral cochains, and then S is a degree K minus 2 real cochains. Okay. So then if you take the co-boundary, then D square is 0, and then delta D we have. Then rewriting, we have integral omega prime minus C prime equals to integral omega minus C plus delta D, if and only if integral omega prime minus omega equals to C prime minus C plus delta D, right? Okay, now this implies, by the fact I said, which is going to be useful, this omega prime must be identically the same as omega, and this C prime and C must be the same up to D something. So the cohomology classes are the same. So that proves that if you choose different lift T prime, that doesn't alter the map I and R. Now, I'm going to look at why I and R are surjective. So this is an exercise to show that given omega that's in closed forms in degree k with integral periods, there exists u in this degree k integral homology such that, so you take u and then realify it. So you send it from this integral homology. So if you have u here, then map it here by r of u. So such u exists, such that is the same as integration of omega in take cohomology class. Well, proving this is also not that difficult. If you take this thing and then take delta, then this thing should be, you can rewrite in this way. So, and this must be integral cochain. And then at the same time, this D and D commutes. Then this must be 0 because this closed form. So that means this is cocycle. So the thing, I mean, this real cochain, this is actually cocycle, and actually this is not just integral. That's not just real chain, but it's actually real cochain. But this is actually integral cochain. So we take this fact and then let this U to be integral cohomology class represented by some integral chain C as before. Then C minus integral omega would be delta lambda for some now I'm looking at things inside real cohomology, right? So I wrote C here, but actually I'm thinking of that as a real cochain. This is also real cochain because like to realification is considered. So for some lambda in degree k minus 1 m r, then we define this chi to be what? This consider this lambda, and then you restrict it to degree k minus 1 cycles, and then modulo c. So that means R is onto, right? So I started with this omega, and then I took the pre-image whose image under R is exactly omega. So now for IMAP, given any C in degree K integral cohomology, well, this holds as real cochains. If you use drum theorem, there exists omega, which is closed differential form, degree K, such that integration of omega minus C equals to delta mu, right? Okay, so then define chi to be this mu restricted to C, to this K minus 1 degree K minus 1 cycles modulo integers. So then that's the pre-image of this cohomology class in integral cohomology class. So I is onto. So for the remaining parts of hexagon diagram, I'm gonna do the following. I'm gonna leave many things as exercise. I think I already have done the most technical parts of these arguments. The rest, I think, students can fill out details. So there's this map E, which is degree K minus 1 cohomology with coefficients in R mod C that goes into H hat K of M. So what you do is you take this cohomology class, and then you pick the representative X. So this is defined on degree K minus 1 what? So I mean this is what? This is degree K minus 1 cocycle, right? Then it is actually defined on chains, but then you restrict that onto cycles, degree K minus 1. Then you'll see this is actually a map from K minus 1 cycles into R mod C, right? So as you have seen in the definition of H hat. Then differential form, you take just 0. Okay. Then what you have to do is that show that E is well defined. Right? So to define this map, you have to make a choice, but it is almost obvious that this map doesn't depend on your choice. For example, if you take x plus delta y, the delta y actually gets killed. And also, this is 1-to-1. So I think this might be a little bit tricky. So one proof that I remember off the top of my head is using universal coefficient theorem. So it might be beneficial for students if you're new to this topic. Then your first like task would be understanding the universal coefficient theorem for cohomology. Then this is gonna become more accessible. So this first exercise, second exercise is that you want to show that the diagonal sequence is exact. So image of E is the same as corner of R. And this is easy. You just have to look into definition and easily prove it. Now, next exercise is taking degree k minus 1 differential form that goes into h hat k of m. What you do is take differential form alpha, and then you send it as follows. You first take alpha and integrate it, and then restrict it to degree k minus 1 cycles, and then modulo z. So then you can see this is actually a map from this to Ormat z. Then here you put d alpha. So then for this definition, there's like no well-definedness you should check, but show that first corner is omega k minus 1 closed differential form m with integral periods, right? Actually, this is almost obvious if you look at how this map is defined, and then this becomes 0. 0 means alpha is closed, and this becomes 0 means you remove this twiddle, and then equivalently you say that this is valued in integers. So it's obvious, right? And second, then you have this A map defined on omega k minus 1 of m modulo corner that goes into h hat k of m. The map is defined on this. Then show the image of A is actually corner of I. Yeah, it's not also difficult to check. It's just some minor details. Now, you have this h hat in the middle. Then you want to see these triangles are commutative. So this is E map. And this is minus Bochstein, and this is degree k integral cohomology, and this is I map that we define, and this is R map we define. This is degree k closed differential forms on M with integral periods, and then this is no. Okay, we just put only that, and here is the A map, we just have seen. Closed integral periods. And this map is D. So show that this is commutative and this is commutative. So that's the exercise. Yeah, it's also not difficult. And then for the squares being commute, I wouldn't even put that as an exercise because it's very easy. Because I think this equation itself would mean that the right square commutes, right? This square commutes, and then these scalar commutes being almost tautology. So only thing that you will need to check is that you have to look at what actually the Bochstein map does. Actually, basically takes the co-boundary of your thing. Then really you go in this way, then the minus Bochstein gives you exactly the same image. That might be, I mean, not much of work, but something slightly less obvious than the rest. Okay, and this thing is an exercise. I wouldn't say this is difficult, but it's an exercise. Upper, lower sequence are long exact sequences. One way that you can easily check that is that, so you know this diagram's commute, right? So when you want to see this map is a long exact sequence, then for example, if instead of considering this map, you can use this composition as the same as this one, and so on. So that makes your work slightly easier. Okay. Okay, I think I should get toward the conclusion of this discussion and introduce what's gonna come next. So if you look at the definition carefully, then degree zero cohomology is actually zero. Different degree zero differential cohomology. So degree one, this must be smooth maps on M, but valued in Almat C. And so those two are something that doesn't need a lot of work, but the assignment, you take pi naught, i.e. isomorphism classes of principal S1 bundles with connection over M, and you send it to degree 2 differential cohomology. This is an isomorphism. So I mean, this is a bijection. So what's the map? So you take principal bundle with connection, right? Then you have to define this chi, and for this omega, you could just put the curvature. Sorry, just put curvature. So then what's this chi? This gamma is any loop M. So this is defined to be the holonomy of this along this gamma. So then you can extend this definition actually to all cycles by if you have chi of x, if x equals to some gamma plus delta y, then you write you define this to be chi of the loop closed loop gamma plus let's say 1 over 2 pi integral of c d theta y. So in this way, you can define chi that satisfies the requirement from our definition. Um, so given this d theta sitting in degree 2 closed differential form with integral periods, by this proposition, which was an exercise, we know that there exists some C in degree 2 integral cohomology, such that this integral of d theta, then taking cohomology class, is exactly the exactly R of C. So C here classifies P, which is the first Chern class we have seen last time, right? So then you might wonder, like, what's the analog of this proposition? I mean, this one, this proposition in higher degrees, in k equals 3 or higher. So then that has to do with introducing gerbs with connection. And if you want to replicate this story, then here this holonomy of holonomy along this gamma is actually holonomy of connection of your line bundle. But then you should make sense. Why should it be the holonomy of a gerb? And even this holonomy of a gerb and or things generally in here are actually applied even to the study of this mathematical studies of topological insulators, if you have heard of. So if you are curious about it, see Gavesky's work on TI, topological insulators, and gerbs. I don't know. I'll be able to introduce this holonomy of a gerb next time. Time permits, I try to do that, but there are other things too. So I'll see. And just one more remark, and I'm gonna stop. This h hat k of m is determined uniquely by the hexagon diagram. So if you think of two things that fits into this hexagon diagram, so whatever those two groups are, if two things fit here, then they must be naturally isomorphic. So that's actually people would know who's Jim Simons, and then when Jim Simons came back to mathematics in around 2007 or something, the question that he had in mind was this question. This is actually the result of Simon's Sullivan. It's actually their theorem. And then this holds more generally to other generalized cohomology theories, which I'm not going to go into, but it's generalized by Bunker and Schick uniqueness theorem. Okay, I'm going to stop here. Thank you so much.
Thank you so much, Bianco, for the very awesome talk.
Thank you.
If there are any questions, you feel free to ask Professor Park. As usual, I have some very elementary questions.
Sure.
So, do we have a cup product for these?
Yeah, you're asking about ring structure. That's an amazing question. I mean, that's awesome. I mean, sure. Yeah, there is a cup product. I introduced this H hat as groups, right? And there's a ring structure too. And if you look into this Chigger-Simons, I'm gonna actually, I actually didn't mention it ever. What this is, what the title of this thing. So Chigger-Simons, this differential characters. And geometric invariance. So this paper is not tagged, so it's a little bit difficult to read. But yeah, if you look into this paper, they deal with. I mean, they talk about ring structure, and even in this Bunker-Schick generalized cohomology theory, this uniqueness. So they also consider the ring structure. So yeah, but like ring structure. I mean, even in graduate school topology, when you learn first time, like cohomology as groups and cohomology as rings, that's an extra layer of difficulty, right? So here the same. Even like the most closest cousin of differential cohomology, of the singular cohomology, would be like differential K theory. This cup product is not that well understood. I mean, maybe, I mean, in differential K theory, cup product is well understood, but like twisted differential K theory, cup product is, I don't think it's well understood. Yeah, there are many interesting things going on that has to do with the cup product. Okay, so here's a question.
I asked that question because so is the top dimensional, like if you take a four manifold, then the top dimension is one dimensional, the top cohomology, differential cohomology group, is it still one dimensional or is different? Like if you have a n manifold and you take the Hn hats.
Right. So you're. I mean, thinking about that. I mean, that's a good question, and that has to do with this diagram. So, for example, if you have the top dimension, and these things might not be trivial, but it also depends on your what your manifold is, like if it's not orientable.
Right. Okay, so I'm gonna ask other questions later, but there is one question in the chat.
Yeah. This question by Kezra. Elaborate more on the last remark. By last remark, you mean the uniqueness theorem? This thing. Yeah. So Jim Simons asked the following question. He felt that actually the thing in the middle is uniquely determined by the diagram. So that means if you already know if you are given a manifold, um, then you have these corners and you have these commutative diagrams. Then the thing that can fit here uh, is unique. So that's the claim. I mean, that's the statement. So then, if you suppose there exists another group that fits in here, having these corners and commutative diagrams, then they must be naturally isomorphic. And let's see. I don't know whether I should talk about a little bit more about the proof. There. So if you look at this Bunker-Schick uniqueness theorem, then they do more general case subsuming H hat, and basically what they figure out is the axiom. So when the differential cohomology is uniquely determined, so there are conditions. First, hexagon, and second is that has to do with some integration map, so S1 integration. So if you have heard of this push forward or like a Gaussian map kind of thing, it's this one. Third, this is rather technical condition, is rationally even. So they impose, under these conditions, they show that the thing that fits into the middle is actually unique. Yeah. Is that answering the question? Okay, my pleasure.
So, any more questions for Professor Park? Hey, Bian.
Hey.
Hi again. So I know it's late in Korea, so we're not
It's
gonna
fine.
hold you there for much longer.
Let me
I have,
mention one
yeah,
thing. So actually, this paper, two things. One is that if you read any paper written by Jim Simons, those are very well written. It's actually very readable to graduate students. So I think Simons has that kind of thing in mind, that when one writes a paper, then it should be really comprehensive. So he writes comprehensive paper, and so is this paper. So so if you're interested in this area and learn about things, there are at the very least two important papers by Simons. One is Chun Simons. The second thing is Chiro Simons. And I think those papers are amazing topic for your master's thesis or like oral exam kind of thing. And in this paper, these old people, when they write mathematics, they are not like here's a construction and definition, and you do whatever you do and buy. They never do these things. When they write this paper, they do the following. So they give this precise construction, and then they justify why this construction is important, right? It's like they give a bunch of applications, even including index theory and so foliation and embedding of Riemannian manifolds. So by just looking into, learning things in this paper, you can learn lots of good mathematics. Yeah, so I wanted to give that information to students if they're interested.
great, great. Yeah, I definitely should read those also.
Yeah,
I need to.
anyone should. Yeah.
Um, Yeah, thank you so much. It was a great talk. I really,
Thank you.
I'm learning a lot. So yeah, great, great. So are there any more questions? I have lots of more questions, but I don't want to. Maybe I'll ask you next time.
Sure. Yeah.
One was about signature. Like, can you define, like, for four manifolds? Can you define
Hmm.
signature in the like uh, you take the cup product of two degree two cohomology classes, and
Ah, yeah,
then
you're talking about the signature. Yeah, those things appear in Chigo Simon's paper, but I don't remember that off the top of my head because I personally never used those specific characteristic classes. But it's definitely really kind of closely related. So I'm going to look into more details, and if I get to find something, then I'll let you know.
sure, sure. I can email you later. See.
Yeah, yeah.
Okay, thank you so much again. So it was a really good talk, and thanks for your time, Bianco.
Yeah, thank you. And
Um, and we'll see you next
I
week.
know that this is just like a 1 hour or 15-minute talk, but I thought it might be better just rather going slower, but taking a little more time for the audience.
I think your pace is really good because these are hard stuff. So for you, it's easy, but for the audience, I mean, the pace was really good, I think.
Yeah, yeah. I thought because there are students in your audience, so I should be like not like just like throwing words, but more
Mm.
accommodating. I should.
Yeah, yeah, yeah. It was, yeah, you had a proof, like a long proof, and that was great. Okay.
Okay.
So it was great seeing you, Bianco. So
Yeah,
maybe
same here. Yeah, I'll
yeah.
see you
So
next week
are you
with
coming
germ
to
stuff.
Iran sometime soon? Like
Uh,
if
I hope so.
yeah,
Yeah.
yeah, okay. So maybe we can invite you like in near future, and
Mm. Yeah, that
uh,
sounds great. Yeah,
yeah,
you should come over to Seoul too. Yeah,
yeah. Maybe when my son like grows up a little bit, like maybe when he's like 3, 4.
two, three. Yeah,
He's right now he's a mess. So he's just running around and doing crazy stuff.
yeah. Maybe like year later, you might feel different. Yeah. They grow up
Mm.
fast.
Yeah, yeah, yeah. Okay, okay. Okay, so we'll talk later and yeah,
You
thanks
sure? Yeah.
again, Yango. Have a nice
Thank you.
day, night. Take care.
Thank you.
Thanks
See you next
everybody
week.
for
Bye.
okay. Bye.